Section. Introduction. We're going to delve into the world of large language models, which are capable of solving complex tasks by generating solutions in a step-by-step manner. However, these models aren't perfect and can sometimes produce false information, especially when they're unsure. This is particularly problematic in areas that require multi-step reasoning, as a single mistake can throw off the entire solution. To improve these models, we need to detect and correct these errors. One way to do this is by training reward models to distinguish between good and bad outputs. These reward models can then be used in reinforcement learning or to perform search via rejection sampling. However, the effectiveness of this system depends on the reliability of the reward model itself. In related research, two methods for training reward models have been described: outcome supervision and process supervision. Outcome-supervised reward models, ORMs, are trained using only the final result of the model's thought process, while process-supervised reward models, PRMs, receive feedback for each step in the thought process. Process supervision seems to be the better option as it provides more precise feedback and is easier for humans to interpret. It also rewards models for following a human-approved thought process. In the realm of logical reasoning, models trained with outcome supervision often use incorrect reasoning to reach the correct final answer. Process supervision has been shown to correct this misaligned behavior. However, in the domain of grade school math, both outcome supervision and process supervision have been found to yield similar final performance. We decided to conduct our own detailed comparison of these two methods, using a more capable base model, more human feedback, and the more challenging math dataset. Our main findings are as follows. 1. Process supervision can train much more reliable reward models than outcome supervision. Using our state-of-the-art PRM, we were able to solve 78.2% of problems from a representative subset of the math test set. 2. A large reward model can reliably approximate human supervision for smaller reward models, and it can be used to efficiently conduct large-scale data collection ablations. 3. Active learning leads to a 2.6 times improvement in the data efficiency of process supervision. 4. We are releasing our full process supervision dataset, PRM 800K, to promote related research. In our study, we compared outcome and process supervision. Outcome supervision can be provided without humans, since all problems in the math dataset have automatically checkable answers. However, process supervision cannot be automated and requires human data labelers to label the correctness of each step in model-generated solutions. We conducted experiments on both large and small scales. At large scale, we fine-tuned all models from GPT-4. At small scale, we used a large-scale model to supervise small-scale model training. This setup allowed us to conduct several important ablations that would otherwise be infeasible. We used a single fixed model to generate all solutions, which we call the generator. We did not attempt to improve the generator with reinforcement learning. When we discuss outcome and process supervision, we are specifically referring to the supervision given to the reward model. We evaluated a reward model by its ability to perform best-of-n search over uniformly sampled solutions from the generator. For each test problem, we selected the solution ranked highest by the reward model, automatically graded it based on its final answer, and reported the fraction that were correct. A more reliable reward model will select the correct solution more often. All large-scale models were fine-tuned from the base GPT-4 model. The small-scale base models are similar in design to GPT-4, but they were pre-trained with roughly 200 times less compute. As an additional pre-training step, we fine-tuned all models on a dataset of roughly 1.5 billion math-relevant tokens, which we call math mix. This improved the model's mathematical reasoning capabilities. Section summary. Large language models are powerful but prone to producing false information, especially in domains that require multi-step reasoning. Training reward models with process supervision, which provides feedback for each step in the model's chain of thought, can mitigate these issues and improve reasoning capabilities. In this study, we compare outcome supervision, training with only the final result, and process supervision, and show that process supervision leads to more reliable reward models, achieving a 78.2% success rate on the math dataset. We also demonstrate the effectiveness of active learning in improving the data efficiency of process supervision. Section. Generator. We've developed a generator to simplify the process of solving mathematical problems. This generator is trained to provide solutions in a step-by-step format, making it easier to understand each step. We do this by generating solutions to a number of math problems, filtering out the ones that lead to the correct answer, and then fine-tuning the model based on this data. The goal here isn't to teach the generator new skills, but to help it present solutions in a more understandable format. To gather data, we ask human data labelers to review the step-by-step solutions provided by the generator. They label each step as positive, negative, or neutral, depending on whether the step is correct, incorrect, or ambiguous. We allow for neutral labels as they help us handle ambiguous steps better. We've collected a large dataset of these labels, which we refer to as PRM800K. This dataset contains 800,000 labels across 75,000 solutions to 12,000 problems. We also have to decide which solutions to present to the data labelers. We prefer to show them solutions that are likely to trick our best reward model. So, we choose to show them solutions that are highly rated by our current best model but end up with the wrong answer. We believe this approach will provide us with more valuable feedback. We also train outcome-supervised reward models, ORMs, and process-supervised reward models, PRMs. ORMs predict whether a solution is correct or incorrect, while PRMs predict the correctness of each step in a solution. We use the predictions from these models to score the solutions. For ORMs, we use the prediction at the final step as the overall score. For PRMs, we calculate the score as the product of the correctness probabilities for each step. When we provide process supervision, we only supervise up to the first incorrect step. This makes it easier to compare outcome and process supervision. For correct solutions, both methods provide the same information, that every step is correct. For incorrect solutions, both methods reveal the existence of at least one mistake, but process supervision also reveals the exact location of that mistake. This approach keeps the labeling costs similar for humans, as determining the correctness of a solution is equivalent to identifying its first mistake. Section Summary. The generator is trained to produce step-by-step solutions in a desired format by generating solutions to math problems, filtering for correct final answers, and fine-tuning the model. Human data labelers assign labels to each step in the solution, positive, negative, or neutral, to collect process supervision data. The training set contains 800K step-level labels across 75K solutions, and the models are evaluated on 500 test problems. Section. Large-scale supervision. We've trained a large-scale process reward model, PRM, using step-by-step labels from a dataset we'll call PRM800K. To make sure our outcome reward model, ORM, is as robust as possible, we've trained it on 100 random samples per problem from a generator. This means the ORM training set doesn't overlap with PRM800K and is 10 times larger. Even though these two training sets can't be directly compared, each one represents our best effort to push the boundaries of what's possible with each type of supervision. We found that training the ORM only on PRM800K solutions would be problematic, as our active learning strategy has skewed the dataset towards incorrect solutions. We did try training the ORM on a larger set of PRM800K solutions, by adding in randomly sampled solutions, but this didn't improve ORM performance. We also compared the performance of each reward model as a function of n, where n represents the number of solutions considered. We found that the PRM outperforms both the ORM and a baseline method known as majority voting. The PRM not only achieves higher performance for all values of n, but the performance gap increases as n gets larger. This suggests that the PRM is more effective at searching over a large number of model-generated solutions. We also experimented with a method called ERM-weighted voting to combine the benefits of the PRM and majority voting, but this didn't noticeably improve performance. We used a specific subset of the math test set for evaluation, which we describe in more detail in the appendix. We found that the PRM outperforms the ORM at large scale, but this doesn't tell the whole story. To better compare outcome and process supervision, we need to consider two confounding factors. First, the training sets for the ORM and the PRM are not directly comparable. The PRM training set was constructed using active learning, is biased towards incorrect solutions, and is 10 times smaller. Second, grading based on the final answer will give positive labels to incorrect solutions that reach the correct final answer. This could harm ORM performance, an effect we may or may not want to attribute to outcome supervision more generally. Because collecting human feedback is expensive, we can't easily isolate these factors using human labelers. Instead, we use the large-scale PRM to supervise smaller models. This setup allows us to simulate a large amount of data collection at a modest cost. We then conducted a direct comparison of outcome and process supervision. We first sampled between 1 and 200 solutions per problem from a small-scale generator. For each dataset, we provided 3 forms of supervision: process supervision from the large-scale PRM, outcome supervision from the large-scale PRM, and outcome supervision from final answer checking. The only difference between these 3 series of reward models is the type of supervision, as they are otherwise trained on identical datasets. We found that process supervision significantly outperforms both forms of outcome supervision at all data collection scales. We also found that using the large-scale PRM for outcome supervision is noticeably more effective than final answer checking. This can be explained by the fact that the large-scale PRM provides better supervision for solutions that reach the correct final answer using incorrect reasoning. Finally, we looked at the impact of active learning. We trained a small-scale reward model on a single sample from each problem, and used this model to score 1,000 samples per problem. To train each of our larger reward models, we selected n samples per problem such that 80% are the most convincing incorrect samples, and 20% are the most convincing remaining samples. This process ensures that all samples are relatively convincing, that a large fraction are known to contain at least one mistake, and that our overall dataset is not too heavily biased toward incorrect solutions. By comparing the slopes of the line of best fit with and without active learning, we estimate that this form of active learning is approximately 2.6 times more data efficient than uniform data labeling. We also performed a preliminary investigation into the impact of iteratively retraining the small-scale reward model throughout data collection. Unfortunately, we observed instability in this process which we were unable to diagnose. The resulting reward models performed no better than the models described above. We believe that some form of iterative retraining could be beneficial in active learning, but we currently have no concrete evidence to support this claim. We consider this a compelling direction for future research. Section Summary. The authors trained a large-scale process reward model, PRM, using step-level labels and a large training set called PRM800K. They also trained a large-scale outcome reward model, ORM, on a larger training set that had no overlap with PRM800K. The PRM outperformed the ORM and majority voting in searching over a large number of model-generated solutions. Additionally, the authors compared outcome and process supervision using smaller-scale datasets and found that process supervision significantly outperformed both forms of outcome supervision at all data collection scales. They also investigated the impact of active learning and found that it was approximately 2.6x more data efficient than uniform data labeling. Section Generalization. We wanted to understand how well our large-scale ORM and PRM models could handle unfamiliar problems, so we tested them on a set of 224 STEM questions from recent AP Physics, AP Calculus, AP Chemistry, AMC 10, and AMC 12 exams. These exams were released after we had compiled our pre-training dataset, so we're confident that the models hadn't seen these problems before. We found that the PRM model performed better than both the ORM and majority voting, even when faced with new test questions. This suggests that the PRM model can handle a certain amount of change in the type of problems it's given. One of the benefits of process supervision, which is the method we use to train our models, is that it gives more detailed feedback than outcome supervision. With outcome supervision, the model has to figure out where it went wrong if it gets a problem wrong, which can be especially difficult for complex problems. Process supervision, on the other hand, tells the model exactly where it made a mistake and how many of the initial steps were correct. This makes it easier for the model to learn from its mistakes, which is likely why it performed so well. Process supervision also has several advantages when it comes to aligning AI with human values. It encourages models to follow a process that humans have approved of, making the model's reasoning easier to understand. It also rewards the model for thinking in a way that aligns with human values, rather than just for getting the right outcome. This makes it safer than outcome supervision, which can lead to models that behave in ways we don't want if they learn to exploit the reward system. However, safer methods for AI can sometimes lead to lower performance, a trade-off known as an alignment tax. But our results show that process supervision actually leads to better performance, meaning it has a negative alignment tax. This could encourage more people to use process supervision, which we believe would have positive effects on AI alignment. We're not sure if these results will apply to areas outside of math, so we think it's important for future research to look into this. We should note that the test set for the math dataset, which we use to evaluate our models, contains problems that have been discussed online and may have ended up in our pre-training dataset. We tried to remove all these problems from our dataset, but it's hard to guarantee that we caught all of them. We didn't see any signs that our models had memorized these problems, but we can't rule out the possibility. However, we think any overlap between the datasets would affect all the models in the same way, so our comparisons should still be valid. In related research, other scientists compared outcome and process supervision in the context of elementary school math. They found that both methods led to similar error rates, but process supervision achieved these results with less data. Our research differs in a few ways. We used a more advanced model, we tested on a more challenging dataset, and we collected more process supervision data. Despite these differences, our findings support the idea that process supervision is a better method for training AI models. Section Summary. The authors evaluate their large-scale ORM and PRM models on a set of STEM questions that the models have not seen before, demonstrating their out-of-distribution generalization. They find that the PRM outperforms both the ORM and majority voting, indicating that the PRM can handle distribution shift and perform well on fresh test questions. Additionally, the authors highlight the advantages of process supervision over outcome supervision, including more precise feedback, interpretability, and safety in AI alignment. They also discuss the potential impact of test set contamination and compare their results to related work on outcome and process supervision in grade school math. Section: Synthetic Supervision. In the section titled Synthetic Supervision, we discuss our approach of using a larger reward model to guide the training of smaller models. This is similar to the method used in other studies, where they've observed over-optimization during reinforcement learning from human feedback, RLHF. These studies often require a substantial amount of human preference data, which can be challenging to gather. To overcome this, they substitute human feedback with a gold standard reward model. Our method of using a large-scale reward model to supervise smaller ones shares similarities with this approach. In the realm of natural language reasoning, several recent studies have indirectly related to our work. These studies have shown that when models are fine-tuned on a large body of technical content, their performance on mathematical tasks significantly improves. Other studies have demonstrated that self-consistency can lead to impressive results on various reasoning benchmarks, without the need for any additional fine-tuning. Some researchers have highlighted the importance of carrying out intermediate reasoning steps through a thought process or a scratchpad. This approach is particularly useful for tasks that require multi-step reasoning. Interestingly, some models have shown the ability to perform this behavior without any prior training, responding solely to a simple prompt.